Welcome to the next video. This time I will show you data collection using our Rigaku Synergy Array instrument, and we'll measure some inorganic crystal. It's a Mohr salt, so it's an iron complex. Okay, so let's go for the Crystallis Pro app. It will now make sure it moves to a proper position. I can't show you that, but that's what it's doing right now. Okay, still going. And it should be done now. Yeah. Okay, so it goes to start stop. We start new. I'll just set some random user. Okay, so we press mount. I've already mounted the crystal and more or less centered it. You can see the crystal here, right? You can move it a little bit so you can see it better. It's not perfectly centered, but for our purpose, that will do. Okay, so we can screen it. I always use the star, and we can set our time here. So 0.2 seconds should be enough. Let's do OK and screen. And you should see the diffraction pattern now. As you can see, it's super fast. It's a well-diffracting crystal. It's Mohr salt, nothing complicated. So we can see indexing 86%, which is, well, could be better, but it's literally a crystal taken with a spoon from a bottle with the reagent and then just crashed. So I think that's alright for our purposes. So we can see the diffraction pattern. Okay, it indexes. And it diffracts pretty well, at least up to what we see now. I will show you this option. This is what is this? And basically we ran a very short experiment just to low resolution to see whether the structure will solve, and that's useful sometimes if you want to quickly tell whether your material is there or you crystallize, I don't know, sodium chloride, whatever. So we can do what is this? Okay, we can use that. We can put some element list. I think I should have it somewhere here. Doesn't really matter, something like that, right? And we press start. We don't have to do it, but sometimes it's useful to not waste instrument time. If you find out that, for example, you put the wrong crystal on the loop because there were some crystals that turn out to be sodium chloride or something like that. So you can see diffraction. It doesn't measure all the way to 0.8 angstrom. We're using copper radiation, but that should be enough to solve a structure and get preliminary idea what is happening here. So there's AutoChem installed, which should be now processing the data and trying to solve it with ShellXT. And we can already see that we have iron, we have waters coordinated to iron, we have sulfate, and we have this, well, I think this is oxygen, but this is probably nitrogen from the NH4 plus cation in the Mohr salt. Still collecting and processing it. It will take some time. Okay, I think it finished collecting the data. So we only did 3 runs. and we should be able to open it in some sort of OLX viewer now when it finishes. Okay. Hopefully it will open it. I think I clicked that already. Well, it doesn't work perfectly today. Come on. Okay. Starting Structure Explorer. Amazing. So we can see, yeah, we have iron, we have coordinated water molecules, right? You can see hydrogen atoms here. We also have ammonium in here. We can see the other hydrogen, well, at least yet, but that looks fine. Okay, I will close that. And now we would normally run pre-experiments to estimate how long is our data collection going to be and choose proper strategy. I will show you one thing first. So we have an iron complex, and we don't really see it with such low exposure times and at these detector positions, but iron tends to have some fluorescence with copper radiation. We can see that by running a new experiment. I will do it as a pre-experiment. So let's call it my initials WS test 1. There is some old data with that name. And let's try to collect it with 1 second exposure. So we're now running pre-experiment to estimate how good is our crystal and then try to see what's going to happen with the suggested strategy to collect data. I don't want to run AutoCAM this time because we already know what's there. Okay, so start and execute and start the experiment. And let's see how it's going to look like. And what you can see here is exactly what I wanted to show you. This high background visible at higher angle detector position is fluorescence of iron. Now, probably here it wouldn't be a terrible thing to measure it like this, even if you really needed to go for such long exposure time. That's 1-2 seconds depending on the detector position, because as you could see, our sample diffracts pretty well. But if you had some samples that you really need to measure for a longer time, you need very good high angle data, that is a little bit problematic. I will stop it for now, and I will show you what we can do if we have iron in a sample and want to get rid of this fluorescence signal. We go here to the hopper, and our detector, Hypix 100, offers us an option to set up energy discrimination. So we will filter this fluorescent signal of iron. We will, because of that, also remove some intensity from our proper signals. But if we have a well-diffracting sample, we can sacrifice a bit of that, and you will see how much better it will become if we do that. For iron, we can set it to something like 7.8 kiloelectron volt threshold, okay? And now I will run the same type of experiment. I will call it again WS test 1, get last used formula, and I think we use 1 second exposure time. And okay, let's not run AutoCAM and exit and start the experiment. Let's see how different it will be to the previous one. Normally fluorescence is seen more in the higher angle, and that's the high angle detector position. You can see that here we don't have that problem anymore, right? We were able to remove this fluorescence signal of iron by using energy discrimination option on our detector. I will stop it, we don't need it right now. Okay, again, with our very small exposure times, we don't really see much of that, but we could also measure it like this. Why not? Okay, so I will go now to start new. And okay, let's do some screening and then run the experiment again, but with more reasonable exposure time. Okay, again, I will call it in the same way, WS test 1, clear folder. Okay, 0.8 angstroms, and let's say we will run it with something like 0.4 second exposure. Why not? Complete data for publication up to 0.8 angstrom resolution. Let's say that we want to achieve 25 I/sigma, and we'll run interactive strategy after the experiment. So, okay, let's exit and start the experiment. And let's see. So our detector is moving a bit. Same with our sample. And let's run this quick experiment and decide what to do next. Well, so far it indexes nicely. Well, now it dropped like 90%. We'll see what happens later. So we have about 100-ish reflections measured and indexed about 89%, not too bad. We can actually see the live view of the crystal. That's our crystal. And during pre-experiment, we're basically running 6 runs. You can already stop that after 5th, usually, but let's let it do that. So now we see the strategy. So our software suggests us that we'll be able to go to about 0.8 angstrom resolution with exposure time of 0.06 seconds per frame for all the theta positions. We have Pilates, we have 2 upon M symmetry, and here we can see that we'll reach this, well, 99% completeness at the end. Okay, we can also have a look here, but we can see that, well, we're not really reaching 100% completeness for the highest angles, right? We can change that. So firstly, we can see what's going to happen if we run different time for each theta position. So we could run it in a way that we measure low angle with 1 exposure time, and then we measure high angle with higher exposure time. What's going to happen now if we do that? Update completeness. It doesn't really change that. If we change exposure time, for example, 0.1 seconds, 0.2 seconds, you can see that already our I/sigma gets better, calculating new strategy. So we are getting better I/sigma, but our completeness at highest angles is still relatively low. So instead of measuring with the detector distance that we have right now, in most of the cases, if that would be very close to 100%, that's how we would measure it. But if you want to have very nice data set up to highest possible resolution, we can firstly increase the detector distance. But because we increase the detector distance, some of the spots would go beyond the detector and we wouldn't be able to measure them, right? Like we were able to with this, I don't know, 35 millimeters. If you go to 60 millimeters, to catch everything, software tells us that we need to run it for 3 different detector positions. Okay? So we can just adjust the time for this individual I over sigma to be somewhere similar to each other. Let's see, 0.2, calculate new strategy. Okay, we can also increase it a bit more, why not? Okay, now our experiment time got longer because we need to measure more frames, right? We have now 3 different detector positions, but let's see how did it impact our completeness. You can see that we went to basically 100% at the highest resolution. So it seems that our strategy is quite good. Now we are getting I over sigma overall about 45. Because we don't want to measure so long, I think we can, the minimum is 0.08. So let's do 0.08 second. Here, higher angles will do, this position will do 0.16. And here we can do, okay, let's do 0.16 as well. So calculating strategy and the incompleteness, everything looks fine. Experiment will take 13 minutes. Now, it takes 13 minutes to run it, assuming that it's monoclinic P. Now, it's always better to collect more data if we have time, right? But we could now change it to symmetry to 1 and calculate new strategy, and that would increase the time. But there are some risks with respect to that. So what I always do is I first log the strategy. Now it's logged, and it knows that it takes 43 runs to measure it with 2 upon m symmetry, right? We can now change it to 1, and we can see now that to measure hemisphere, it will take 163 runs and overall 47 minutes. Now, it's very useful to do that because, for example, especially if you measure for longer time, you might get some icing issues, or I don't know, your crystal might fall down, something will happen to the X-ray source, filament will break, there will be no electricity, or things like that. So it's always better to run the first unique data set first, and then to run everything else. Now, of course, also our completeness is different because we change it to triclinic. It will not reach 100% completeness for the triclinic, but from the solution, we already know that from this, what is this? We already know that it's a proper symmetry 2 upon m, so we don't need to care about this. It will get 100% for monoclinic strategy. Okay, so we could essentially run it like this, and just remember that, for example, after this, I don't remember what was there, 50 runs or something. After these 50 runs, we could essentially, if we are happy with the data, we could stop it and be happy. But if we have more time, it's less than 1 hour, we could run it, we could run whole hemisphere. Okay, so we have it all updated, sorted out. Yeah, we can just make sure that it will record a movie of the crystal, and we can restart the experiment. It will be now collecting images. in case you need to do some phase indexing to correct for absorption in this way. This is actually a pretty large crystal for an iron complex for such an inorganic salt. So to compare, the loop size is 50 microns. We should be aiming with this instrument to try to get the crystal with size of the loop. Of course, if our crystal doesn't diffract too well, we need to go for larger size or longer exposure time. Okay, so it's still running the images of our crystal. Let's see the first diffraction frame, and then we can stop with our movie. And for the diffraction pattern and the whole data set, I think I will upload it later to Zenodo or some sort of repository like that, so you can download it and play with it if you like. Okay, so thank you very much for watching the video. I hope it was useful to you. Especially I found this option with energy discrimination quite useful sometimes, so I hope it will be useful for you as well. Thank you very much, and I'm looking forward to hear if you liked the video, so feel free to leave any comments. Thank you.